Welcome to Aerodynamics class number 146. In this podcast, we're discussing a new way of starting vertical axis wind turbines. So there are a few different ways to start a vertical axis wind turbine. So if you have a wind turbine somewhere and the flow is not going, it means that it's stationary. Then when the flow starts to pick up, it needs to start. And one simple way of doing this is that they have internal devices that spin the blades. While this is effective, it doesn't utilize the airflow hitting the blades to begin with. Then once the blades are rotating, this air can then be used to produce the electricity we want. Another way to get a vertical axis wind turbine to start is to design the blades such that they can generate enough force with a slow wind speed to start turning and then getting up to speed. With the second way, there are two general approaches. The first is when the blades produce drag, and that drag is the force that is used to rotate the blades. The second way is when the blades produce lift, and that lift is the force used to rotate the blades. So for horizontal axis wind turbines, which are the wind turbines we see in like pictures everywhere, if you go, for example, in the Dutch countryside or whatever, and you see those like little ridges with all these wind turbines along them, or in fields, they're almost always horizontal axis wind turbines. But vertical axis wind turbines are where you have the wind turbine going straight up, then you have the blades around it concentrically, and then they go around in a clockwise fashion or counterclockwise fashion from above. They don't spin around like a clock. It's more like you have to look down on it to see them spinning around in that direction. So this second way, where we have the blades producing lift, that is the way that horizontal axis wind turbines always do it pretty much. But for vertical axis wind turbines, we're a little bit spoiled for choice, really. Like we can have the blades producing drag and or lift. And this method where we produce both drag and lift is quite a new method. And there is potential for it to be more beneficial or more advantageous than just producing drag or lift. So in figures 1 and 2, we can see the difference in how these different blades look. So if you listen to this podcast on Spotify or Google or whatever, you can watch the accompanying video on YouTube and Spotify. So you can see what we're looking at here. So these figures show that while the blades that produce both lift and drag, and then the blades that only produce drag, they look similar, there are some differences. So the blades that just produce drag, which are figure 1B and figure 2B, we see they're effectively like half oval shaped. And the way that this works is like, if you think of a like a little home wind speed anemometer where you have like those little cups on the end, that's effectively like this, but it's in 2 dimensions. So the air comes in and hits them and then spins them around, so they produce drag. However, the blades that produce both lift and drag now feature these semi-oval shapes, but they also have an airfoil profile on the blade tips. So we can see in figure 1A here and figure 2A here, we see these airfoil profiles. So it's not that difficult to see why you'd want airfoil profiles here, so let's discuss why. So at the blade tips, we now have these geometries, these airfoil profiles that produce lift. So the air comes in and then the lift gets produced vertically to the direction of the airfoil. Now these airfoil profiles are uncambered, which means that when they are facing the wind straight on, there is no lift being produced, or at least very little lift, because there might be some interference from the rest of the blades, so that might change the flow field a little bit, change the angle of attack that the airfoils are seeing, but ideally there is no lift being produced at this point. So we have here, for example, we have the flow coming in, it hits this front airfoil, the front of it, and because it's at a 0 degree angle of attack, there is no lift being produced. Similarly, when the airfoil is at 180 degrees, there is no lift being produced because, again, there is no effective angle of attack here. So to produce appreciable lift, the airfoil profiles need to be pitched a little to the oncoming flow. This will only happen when the blades have rotated and are now pitched at an angle to the oncoming flow, and hence these airfoils attached to the blades will produce this lift that we need. So we have these airfoils here now, and the air comes in. You can see that the angle of attack is now non-zero, and this will now produce some amount of lift. So also these blades have a NACA 0018 airfoil profile. This is the ones that they're using. This profile is quite thick, which means that they will stall at a higher angle of attack and have a more gradual stall pattern. So that means that we have a bit more of a buffer in terms of where we can use them. So if we had a very thin airfoil, for example, a NACA 0006 or even lower like 0002 maybe, then that means that when we go to a moderate angle of attack like 5 degrees or 10 degrees, that the airfoil will stall, and that means we don't get lift, then that's not great. So looking at figure 1, we can see that the direction of the lift generated is towards the axis of rotation. So we see here, we have the airfoil pitched here, the air comes in, the effective angle of attack means that we get a low pressure zone on here, and that should drive a force towards the axis. We'll see a little bit later what the flow fields look like, and we'll get a better appreciation as to when the airfoils are producing lift and under what conditions. So interestingly, I expect that when the blades rotate enough, the resulting pitch angles of the airfoils will be large enough to cause stall. So for example here, the effective angle of attack is maybe 45 degrees. That is probably enough to get the airfoil to stall. So this renders the airfoils largely stalling, and that means that these airfoils are really just producing drag. So it's additional drag that we have produced as well. Then once the blades have rotated more, the pitching angle drops enough to the airfoil for the airfoils to then start producing lift again. So once it gets to maybe about here, again it's backwards, but the airfoil still produces some amount of lift. So this approach, as I mentioned, is quite new. So that is what we're looking at in this podcast right now. And to do so, we'll be looking at a paper called A Study on Aerodynamic Characteristics and Visualization of Flow Field of Lift Drag Combined Starter. It's open access, so you can find it in the link in the description. So these researchers aren't looking into optimizing the geometry of these blades, but rather a more fundamental approach of looking into the flow physics around these blades. So as I mentioned, because they are new, the flow physics that these blades with these airfoils are producing are a little bit unknown, so they're looking into that. And effectively we have the old drag-based blades plus these lift-based airfoils interacting together and having some kind of synergistic effect, hopefully. So to do this, they are looking at two different methods, CFD and PIV. So this is pretty cool because being able to validate CFD with PIV data makes your CFD even more trustworthy. So let's discuss each setup. Let's discuss CFD first. So for their CFD, they used ANSYS and have a domain where in figure 3 we can see the domain, where the wind turbine was 5 diameters downstream from the leading edge, from the inlet I should say, and 10 diameters upstream from the downstream, the outlet I should say, trailing edge outlet. I'm getting mixed up there. Anyway, it was also 5 diameters from each side of the wall. Another thing to note is that this CFD uses a sliding mesh approach, and a sliding mesh approach is where you have this where you specify one circular region and actually have it rotating with each time step. So you can see here they have like this circle that they have denoted as interface, and then inside there's the rotating domain. That rotating domain is that sliding mesh I'm talking about. So in terms of simulating rotation, this is a very good way of doing it, and with this particular setup it's perfect. There is no better way to do this. Other methods include rotating walls and multiple reference frames, but these are simplified approaches that also reduce accuracy. So the sliding mesh approach is where you literally have this rotating domain here, and with each time step it will rotate around physically. And because this domain effectively is isolated from the rest of the domain, the cells in here can then just rotate, slip across, and then the information from this domain gets shared with the larger domain that it's effectively part of in the grand scheme of things. So these researchers used URANs. In fact, they didn't actually specify that they were using URANs, but from their setup and finer details, I'm quite certain it was URANs. For example, they said that they used the RNG K epsilon terminus model, which means that they either used URANs or DES. But then they go on and say that they used a simple algorithm, which means that they probably used URANs and not DES. So URANs is less accurate but faster of the two approaches. For their mesh independent study, they looked at 5 different levels of fineness, which is pretty good, but there is a problem. So this mesh independent study isn't the best, and I mean that because while they looked at several different levels of fineness, they never really got to the point where the torque coefficient, which is the value they used to determine whether their mesh had converged or not, whether this value became independent of the number of cells or not. So the values for the finest and second finest meshes, which are these two here, were still 2.3% different in the torque coefficient value, which isn't huge, but it definitely isn't nothing. So whether you can say that this CFD has converged or not, I would probably say no, not yet. It needs to have a finer mesh, but that's what we have at the moment. The good thing is that they do have PIV to help with the validation of their mesh, so let's move on to that. So for those of you who don't know what PIV actually is, the operations principle is very simple. It stands for particle image velocimetry, and this is where you literally just dump a bunch of tracer particles into the flow. These are little particles that will reflect light. Then you shine a laser sheet through it at the point that you want to see. So if you have, for example, this domain here, and you want to see what is downstream, you just shine a laser sheet down here, and then these particles will then start to reflect this light. You then take 2 quick pictures of the light sheet in very quick succession, so maybe separated by 0.1 microseconds or 1 microsecond or whatever you want. So then in those pictures, you'll see the light that those particles have reflected. And if you look at the first picture and then the second picture, you can then see where the particles have gone in that split second between the 2 pictures. Then you can determine each particle's velocity. So that means that's how we get particle image velocimetry. So when you process this data, there are a few more steps that you need to do to reduce the errors. But what I just mentioned in terms of the method is just the general method, and that's how it works. It's quite simple. It's just a laser sheet and some particles that reflect the light and a camera. So once you have that, you're good to go effectively. So what these researchers did was that they had a low-speed wind tunnel and put these blades into them. So the blades that only produce drag, and then the lift and drag producing blades. They then seeded the air and shone a laser into it to illuminate the particles. They then did PIV. One thing to note is that the flow of the speed was 4 meters per second. So the flow speed was 4 meters per second. And while the flow speed may seem somewhat trivial, when it comes to PIV, the flow speed is very important because it can determine whether the PIV works or not. The reason why is because if the speed is too fast, you won't be able to take 2 photos in the time it takes for the particles to travel through the laser sheet. So you take one photo, for example, and even if you take a second photo and you capture some of the particles, let's say 50%, that's still usually not enough to be able to do PIV, because then you're trying to trace where the particles have gone. But because so many particles have fallen out of that laser sheet now, it's difficult to tell whether where these particles have gone really. So you really want to have like 95% of the particles to stay within this sheet during the time that you've taken these 2 pictures, which means you need to take the pictures very quickly and or reduce the velocity of the wind tunnel. So that's why they went with 4 meters per second right here. So another thing that's interesting to note is the particle size. So they don't, I don't know what particles they actually use, but they say the particle size is between 8 microns, I should say, and 12 microns. So this is a pretty decent size. These particles will fall out of the air within about an hour, but they are okay in terms of PIV. So in terms of PIV, the particle size is, again, a balancing act between having them small enough so that they follow the flow, what we call faithfully, which means that they will follow the flow as they should be doing, and they will stay in the air, but also large enough that they will reflect the light. The smaller these particles are, the less light that they will reflect, and the less light they will reflect, the stronger the laser needs to be, and or the more sensitive the camera needs to be. If we make these particles too big, then they'll start to fall out of the air, and they won't even follow the more turbulent regions, because the centripetal forces on them will then make them fly out, and they won't follow the flow properly. So that's the balancing act there. In terms of 8 to 10 microns, that's pretty decent. So let's move on to the results now. So first they looked at the static starting characteristics. So that means that they had the airfoil, so they had the wind turbine not rotating yet, they just have it completely stationary. And this makes sense because when you're out in the field, you have these wind turbines stationary, and to start them, they start from stationary. So they looked at how these blades, the floaters of these blades when the wind turbine started up. The point at which the blades start to turn is when the torque produced exceeds the internal friction drag of the turbine. And the non-dimensional number is the non-static torque coefficient. So this number will change depending on where the blades are located in the axis. So for example, if one blade is located at the front of the axis and the other one is located at the back, the forces the blade produce will be different to if the blades were located on each side of the axis. This is simply because the geometries that the oncoming flow is seeing are different. So I should probably just come back up to this picture and just explain this a bit better. So if the airfoils are on the side, for example, these airfoils will produce different, and these blades as well will produce different forces compared to if they had rotated another 45 degrees, for example, or 90 degrees or whatever. That's just how the geometries work. So figure 7 shows the results with the different starting angles around the axis. So we have the red line, which is for the blades that are producing both lift and drag. So that's figure 1A here. These blades here. Figure 1B, which is just the drag producing blades. There is no airfoil in the end. That is shown by the black line here. So we can see here. And on the y-axis we have this starting torque coefficient. And the lower this value is, the easier it is for this blade, this wind turbine to get started. So interestingly, both lines follow a similar trend, but there is definitely an offset. So we can see that the red line here, the minimum occurs at about 120 degrees, whereas for the black line, which is the drag producing blade only, the minimum is about 80 to 90 degrees. So this offset is due to the addition of these airfoil profiles on the blade tips that alter the overall force generated. One thing to note is that at 0 degrees, when the blades are on either side of the axis, so this is where we have this exact setup here. Let me just scroll up. So we have this blade on one side, then the other blade on the other side. For this axis, that's at 0 degrees. Then at 90 degrees is where we have one blade at the front, one blade at the back. So in other words, we can kind of tell that for both of these blades, these blade types, when we have one airfoil at the front, one airfoil at the back, that's when we're starting to get about the minimum static torque coefficient, which means that we're getting the lowest amount of resistance to rotation. So for both the drag and the lift and drag producing blades, the best angle, i.e. the angle with the lowest static torque coefficient, hovers around when one blade is at the front and one blade is at the back. When the blades are on either side of the axis, the static torque coefficients are considerably greater, which means that a greater wind speed is required to get this turbine to start turning. Interestingly, the blades that produce the only drag generally have a lower static torque coefficient than the blades that produce both lift and drags by this black line here. In figure 8, we can see the CFD and PRV for when the blades are at 0 degrees, so when they are on each side of the axis. So one at the top, one at the bottom here. One major difference between the drag producing blades and the blades that produce both lift and drag is that for the blade on the left side of the axis, so this one here and that one down there, the airfoil is effectively pointing downstream, and we see very low pressure on the outside surface of the airfoil. So just here we see very low pressure, whereas here there's no low pressure zone. We don't get that low pressure zone for this drag only blade, so that makes sense kind of, because if we look at the flow coming in to this airfoil, we can see it's skewed. So effectively this airfoil is seeing a non-0 degree angle of attack. The effective angle of attack is not 0. So that means that this airfoil is producing some amount of lift, as we can see by this low pressure on top, high pressure underneath. So that's why we get this change here. Also, for the blades that only produce drag, we get a much higher pressure inside the oval part of the blade facing downstream than for the blade that produces lift and drag. So we can see here, we get really high pressure. And if we go to the PIV, it kind of makes sense why we get that high pressure. So if you see here, these arrows, they tell us not only which direction the flow is going. Let me zoom in so I can describe it to you a bit more. So we see these arrows here. These arrows show where the flow is going, but also the magnitude of them is reflected by the length of these arrows. So you can see here, this arrow right here is very long, and that indicates that we have a very fast moving flow here, relatively speaking. This arrow here is just a dot. That means that the flow is not moving very fast at all. So what does this mean? If we compare these two blades, we can see that the flow inside the drag only producing blade is a little bit slower than the other one, and that indicates that, okay, we probably are getting a higher total pressure and a higher static pressure in this because the kinetic energy from the flow is being dumped into the blade, and that results in the dynamic pressure being converted into the static pressure that we feel. So that's, I think, what's happening here. And while we do get these differences in the pressure distributions, figure 7 shows us that the static torque coefficient is at this angle is pretty much the same for these two blade types. So 0 degrees here, the black line and the red line both coincide at about the same amount. So I guess we can say that these differences in the pressure distribution largely cancel each other out for the moment. So that's quite funny. Something else that's interesting is that if you look at the PIV, so again, this right part here, you can see that for the blades that are pointing upstream, so this one here and this one here, behind them, the flow is almost stationary, which shows a very strong localized wake, especially for the drag only producing blade. So let's move on to some angles where the flow physics and static torque coefficients are different significantly. So in figure 11, we have when the blades are at 80 degree angle of attack down here. And this corresponds to when the black line, which is the drag only blade, is producing the lowest static torque coefficient, while the red blade, and that we get a static coefficient of only minus 0.06. On the other hand, the blades that produce both lift and drag have a static coefficient of about 0.07, which is near the maximum. So these are pretty much on the two opposite ends of the spectrum in terms of their performance. So given how different these two values are, I expect a very large change in the flow physics, and figure 11 shows exactly that. So let me scroll down there here. Okay, so for the top ones are for the blades without the airfoil profiles. The bottom ones are with the airfoils. So for the blades that only produce drag, these top ones, the flow physics is very different. First of all, the pressure distribution is fairly uniform, hovering at around a 0 pascals gauge. So you can see it's mostly green with a little bit of blue and a little bit of red. Whereas for the blades that produce little lift and drag, there is still significant differences in the pressure distribution, with a maximum seen in the downstream blade of 18 pascals, so right here, and even we get some slight increases, or slight drops in the pressure around certain regions at about -14 or so. What's more, the wakes from the drag only blades are much smaller than from the lift and drag blades. So you can see here in the PIV, the wakes are, okay, it's a decent amount, but when you go to the lift and drag producing blades, they're huge. Like the wake is about almost twice the size. So accompanying this reduced wake size is also the fact that there seems to be several vortices, and interestingly, these vortices also appear for the lift and drag blades. So you can see here we get 3 vortices effectively, 3 vortices, and then downstream we have 2 vortices here, 2 vortices here. The only difference is in this downstream blade, we get 2 vortices for the drag only blade, but none for the lift and drag blades. So the fact that these vortices are spaced out more for the lift and drag blades, so here we can see they're spaced out more, is not that surprising considering that the wake is much bigger, but the fact that we get pretty much the same flow features is surprising. So again, they're almost identical except for these 2 little vortices in this downstream blade. So the same vortices pretty much still exist, but they're just stretched and manipulated differently, which makes sense because we have different wake sizes. Now let's move on to where the blades are at 120 degrees. So the reason why I want to do this is because figure 7 shows that this is another point where the drag only blades and the lift to drag blades produce very different static torque coefficients. So you can see here, the red line is down here at about -0.4, while the black line, which is for the drag only blades, is now up to about 0.05. So again, they're kind of at opposite ends of the spectrum in terms of the performance. So flow physics is shown in figure 12 for this angle. Let me scroll down to that now. Here we go. So here we not only get significant differences in the pressure distributions, but also in the general flow fields, so both the CFD and the PIV. So firstly, the pressure on the upstream blade is completely different. For the drag only blade, we see a high pressure of about 14 pascals, so just here, in the blade cavity, while for the lift and drag blades, we see the exact opposite of -14 pascals. For the downstream blades, they also produce quite a different pressure distribution, with the drag only blades producing almost 0 gauge pressure. So here we see is like green, while for the lift and drag blades, we are seeing -10 pascals being produced. So that's quite a lot. In addition, the PIV shows that the angle at which the flow leaves the upstream lift and drag blade is significantly down. So we can see here it's down at an angle, while the same wake of the drag only blade is horizontal. So that means that we get a difference in the lift that's being produced. This also coincides with the vortices produced being much greater in size for the drag only blade than lift and drag blade. For these graphs and figures, we can see that there are significant differences in how well each of these blade designs act as starters, as well as why. But what about the dynamic performance? So we looked at the torque of the blades producing when they are just static and just starting up. But what about once we have 1 revolution, because that is also part of the startup phase. So figure 13, we see the rotational moment coefficient of the drag only blades and lift to drag blades. For this figure, the higher the better. The more torque the blades are producing means that we get a greater moment coefficient, and that means the better the blades are performing. Now we see quite a different story when the lift and drag blades are better. With the lift and drag blades are better than the drag only blades for much of the rotation. Also, we can see here the red line here, which is for the lift and drag blades, it's usually significantly higher than the black line. There are only a few regions where it's lower, and often not by as much as what it is higher than. Also, the minimum rotational moment coefficients of these 2 different types of blades were very similar, hovering around -0.05 here. But the maximum rotational moment coefficient of the lift and drag blades is significantly higher than the drag only blades, being 0.12 compared to 0.08 respectively. So that means that the maximum rotating moment coefficient of the lift and drag blades produced is better. Looking at figures 14 and 15, the differences in the pressure distributions between the drag-only blades and lift-to-drag blades are much starker than when the blades were stationary. So primarily, the lift and drag blades typically produce lower pressure. So we can see here this much lower pressure region over the downstream blade compared to the drag-only blade. And if we go to figure 15, which is at a different angle of attack for 120 degrees, again we get a much lower pressure region. We get 4 low pressure regions here as opposed to just 1 or 2. So we can see why the lift and drag blades could be more favorable than the drag-only blades. Sure, when they are static, there is a case to be made where the drag-only blades are better for starting vertical axis wind turbines, but when they start to rotate, the lift and drag blades are definitely better. Also, this study didn't take into account optimization, so it's anyone's guess as to which blades are better overall. We were just looking at the general flow physics. But what we did learn is that putting tiny little NACA 0018 airfoils on the ends of the blades has significant effects on the blade's starting performance, both when it's static and rotationary, sometimes for the better, sometimes for the worst. And with that, my little aerodynamicist, we come to the end of this podcast. If you liked it, give it a like, and if you want to see more like this, click the subscribe button or the follow button, whichever platform you're on. And if you have any questions about the design, about this, let me know in the comments below. And if you want to get better at CFD or theory, check out our courses in the link in the description. We do courses on CFD for aerodynamics, and like we teach you the right way and how to do it, and like for example the different nuances in terms of meshing and your solver settings, etc. And with fundamental aerodynamics, we also do courses on that where you can learn about theory as we're going through here in other podcasts, but in more detail, and you learn a lot through those. You can find them in the link in the description. And if you want to make your experiments 2% more accurate, check out the MC Hawk. So it's an instrument we make to accurately measure the density of air. The reason why this is important is because the density of air always changes. For example, if you come into your wind tunnel in the morning, then come back after lunch, the density of air has changed by a few percent in just a few hours. The density of air is affected by the temperature, barometric pressure, and humidity. So having even you in the wind tunnel changes the density of air because you're pumping out heat and more water is going into the air from your breath. And if you have other people there, that's even worse. So this changes the density of air by 2 to 4% quite easily, and between days, weeks, months, and seasons, it changes even more than that. 10 to 15% changes are very normal, which means that you need to take into account these changes in your experiments. What's more, if you don't take them into account, then you not only are you finding a lot of things that aren't really there, they're just random errors, but trying to use the experimental data to validate your CFD won't work, and that is one major reason why so many people have trouble validating their CFD. It's not that their CFD is wrong, it's just that their CFD is not the same, is not using the same density as that as they use in their experiments. So of course they're not going to line up. And if they do line up, then that's going to be for wrong reasons. And it's not going to stay lined up for very long, which is even worse. Because then you might validate your CFD and think that you can use it, but then you start using it and then you get really weird answers and you don't even realize it sometimes, so that's even worse. So get yourself an Amazon Hawk. It makes your experiments and CFD more accurate. You can find it in the link in the description. And I'll see you in the podcast. Peace, amigos.